So in this video, we're going to talk about the topic of strain transformations and the concept of principal strains. So these formulas for transforming strain and to find the principal strains are going to be very similar to the transforming stress. So we're going to go through this pretty quickly. So if you're given a strain in the known coordinate system x, y, and z, and you know the directional cosines that relate the xyz coordinate system to the x prime, y prime, z prime coordinate system, you may use this following equation to do that transformation. All right. In a similar fashion, if you're given your strain matrix in any coordinate system, you may find the principal strains by taking the determinant of the strain matrix minus the principal strain variable and setting that equal to 0, and then using epsilon p, you may find your directional cosines or your eigenvectors v. All right. So the critical thing or difference in the case of engineering stress, or in the case of transforming strain, is that we need to use a different strain matrix. So we're used to using our engineering strain matrix, which we have defined here. All right, where we have our normal strains along the diagonal, and then we have our principal strains in the along the in the corners of the matrix. So when we do the stress transformation and we take our principal strains, we need to use a different strain matrix, and that strain matrix is called the elasticity strain matrix. Okay, and the elasticity strain matrix has nine components. All right, 6 unique components, just like the engineering strain matrix. The only difference is that the normal strains are exactly the same. All right. The only difference is for the shear strains in the elasticity strain matrix, the values of those are engineering shear strains, gamma xy, gamma xz, and gamma yz are all going to be divided by 2. Okay? So we're going to have, and then again on the bottom part of the matrix, we'll have those same shear strains divided by 2. Okay? So that's our elasticity strain matrix. So whenever you're finding the principal strains or you're doing a strain transformation, again, make sure that you use the elasticity strain matrix. All right. The last thing is you can do is that you can use Mohr's circle for strain. So the only difference is when you draw out your Mohr's circle. All right. We used to have on our x-axis we used to have stress for when we were solving for using Mohr's circles to find or to do any stress transformations, and on our y-axis we had n equal to tau. All right. The only thing we're going to change for the elasticity matrix or the strain matrix is that we're going to use the x-axis will be equal to epsilon, or a normal strain, and then the y-axis will be equal to, instead of being equal to tau, or shear stress, it's going to be equal to gamma over 2. All right? And again, we're going to use the notation where our traditional negative y-axis will be the positive direction for our shear strain, and then our positive normal strains will be along the traditional positive x-axis. Okay, so if you knew, let's say you had a case where you had 2 known principal strains that were equal and opposite. So let's say we had EP1 and we had EP2. We could draw out our equation here, and we would get our gamma max. This value here would be equal to gamma max over 2. Okay, so so if we look at this, I guess the radius of our circle is equal to EP1. All right, so we can say that gamma max over 2 would be um, equal to the radius, which we can say would be equal to um, EP1 minus EP2. So our epsilon P1, so our principal strain, our maximum principal strain and our minimum principal strain divided by 2. That's going to be our radius. So our gamma max in this case would be equal to EP1 minus EP2, all right, or the diameter of our Mohr circle. All right, so we're going to do an example problem where we'll use a strain transformation with strain gauges in order to calculate the state of strain on a material, and we'll use that strain matrix then to determine the state of stress within the material and to determine the principal stresses.